Right. Good evening. Assalamu alaikum. Right. Hope there are some more doing it. We have to start up a new chapter today. We were supposed to have it physical, but unfortunately, we had to make it online because of the weather conditions and all. And moreover, I have been affected actually, right? So anyhow, I can't stop the class, so that I'm having it online. Unfortunately, oh, is it Salha? Salha, who is that? Is it a new student or is any other names? Raihan, Rukia, Farhan, Nabila, Wasu, Munas. More than half has to join. Uh, was this Salha? Is it a new student or is it with any other names? If so, please rename. Otherwise, a thumbs up if it is the same. Yeah, okay, fine. Okay, right. Right. Okay. So, unit number 11, electronics. That is the topic today. Unit number 11, electronics. You don't have your tools on your hand, but still you can go up with the screen sharing here today. And I need you to write down some notes. Okay. I need you to write down some notes related to the lesson that we are doing. And in a short note, we are going to fill it up today. And then you'll be covering it up with your tool. Okay. Right. Electronics. So this is a lesson connected with some sort of smaller gadgets connected in our mother circuit. Simple to say. When you come for the electric circuits, there are some sort of very small electronic appliances connected. Maybe small in size, but they are the ones doing the biggest work. Okay. So we are going to learn about them, some of the major important electronic devices we are going to learn today. Okay. Fine. So let's start off with this way. When we come for the materials, depending on the conductivity of electricity, we divide these materials into three. What are the three? Those that can pass the current well, those that cannot pass the current well, and those that pass a smaller current, simple to say. So materials, we are dividing into three ways accordingly. What are the three? One we term as conductors. Conductors. One we term as conductors. Conductors very well conduct electricity. Conductors, they can conduct electricity very well, while insulators, they can't conduct electricity. They can't conduct electricity. So conductors, they can conduct electricity very well. Okay. Insulators, they can't conduct electricity well. Then what is the reason, we will be discussing. And in between that, there is another material, that is what our lesson is based on, which we term as semiconductors. Semiconductors. Okay. Semiconductors, when you are taking, They are between the conductors and insulators. They are in between the conductors and insulators. That is, conductors, they conduct electricity very well, right? Insulators, they can't. So in between the semiconductors, they can conduct a small amount of electricity. They can conduct a very small amount of electricity. Okay. So how is it happening? Before that, what are the examples? You can see there. Materials that can conduct electricity are known as electric conductors, basically the metals and mixed conductors. Okay. Metals, they are good conductors of electricity. Okay, like copper, aluminium, iron, lead, some examples. And some alloys are there. What do you mean by an alloy? An alloy refers for two or more metals, no non-metals, two or more metals mixed together, combined together physically. Physically, they are mixed up. Okay, and they are formed as a combination. It is called an alloy. They are termed as mixed conductor. Something like brass, pittala, we see brass. Brass is the combination of copper and zinc. And nichrome, manganese are also some examples. So like these mixed conductors and these examples given, they can conduct electricity very well. Okay. So why they can conduct electricity well? That is the point. Now that is, when you come for these metals, metals are made up of anyhow. Any matter you take are made up of atomic particles, right? Atomic particles are there. When you come for these metals, let me take it as the atoms here. These are the atoms. But the thing is, solid atoms when you are taking, you know that they are very closer to each other. But closer to each other when we are drawing, we can't learn the theory here. So we are keeping a small gap between them. And throughout the lesson, this diagram we are going to use. Okay. So these are the metallic atoms, just imagine. Now, you know that an atom is made up of nucleus and energy levels, right? A small part from chemistry. An atom is made up of the nucleus and the energy levels. Shells are there. So atom made up of nucleus and energy levels will be neutral because number of subatomic particles, okay, when you consider protons are equal to electrons. Protons are there inside the nucleus giving a positive charge. Electrons are there outside the nucleus in the energy levels giving a negative charge. And since both of them are equal, total plus minus the net charge when you are taking, that is 0. If there are 10 electrons, 10 protons will be there. So that is 10 minus 10 plus. Okay, then it is electrically neutral. So net charge is usually 0 in a neutral atom. And you know now electrons appear in the shells. They do have a number of shells related to the point they are assigned in the periodic table. Now metals, when we take these metals, okay, within their vicinity, within their structure, the atoms when we consider, outermost shell is there. If it is having 3 shells, third one is the outermost. 2 shells, second one is the outermost. Valence shell. So in this outermost shell, the electrons, what they do is, they just come out. They just come out of the shell. They have the ability to come out. And they will be there here. In between the atomic particles, they appear within the space. I just took a small example for the metals. So you can see here, okay, these electrons, they have the ability to stay there here. And actually staying there here means they have the ability to freely move. They have the ability to freely move. So these electrons we name as free electrons. What electrons are they? Free electrons. Or another word we are using, delocalized electron. What is the word? Delocalized electrons. Delocalized electrons. Okay. So free electrons, delocalized electrons are there within the metallic atoms, between the metallic atoms. Now, these electrons, okay, they are minus charges, right? Minus charges. So, they act as the negative charge carriers. They act as the negative charge carriers. So, we are speaking about the metals. So, these electrons act as the negative charge carriers. More metallic atoms, more there will be delocalized electrons. So these free electrons means freely moving electrons, they have the ability to carry the charges. Okay. So because of they can transfer the charge like this. When these two ends are connected with a potential difference, okay, when these two are connected with a potential difference, right? What happens here? Usually, you know that when you come for a potential difference, there will be a positive terminal and a negative terminal. This is the high potential, this is the low potential. High potential current is passing, low potential electrons are transferred. Now, these electrons, when they come here, okay, when the electrons are coming here, electrons carrying a negative charge, okay, when these electrons come here and the electrons inside the metal, the free electrons, they are also negatively charged. So these negative to negative, minus to minus, what happened? Repel each other. They repel each other. Minus charges to minus charges repel each other. Unlike charges attract, like charges repel. That you know. Okay. So these electrons coming here, repelling the electrons inside, these electrons will be moving to the other side. So by the way, when they are moving, electrons continuously flow. What they do now, they transfer the electrons. So by the way, when the electrons are allowed to transfer through this, in this direction, opposite direction, the current is allowed to move. So this direction, current is allowed to move. So you can see, while the electrons are transferring from negative terminal to the positive terminal to the negative terminal in the opposite direction, current is flowing. So in this way, the metals can transfer the current. Okay. So you see, in metals, you can see now, in metals, these free electrons, the delocalized electrons contribute to transfer the current. Delocalized electrons contributes to transfer the current. Okay, because of their charges. So this is how metals become conductors. Okay. And when you come for insulators, these insulators, they have got very small amount of electrons. Okay, very small amount of electrons. So not at all sometimes. So since a very small amount of electrons are there, okay, and they are also not like freely moving around. Okay, so because of these, they can't help in transferring the current in such a way. They can't help in transferring the current in this way. So then what happens? So there are no more current or no current at all could be transferred. By whom? By the insulators. Why? Because they don't have free electrons. So or else the free electrons are very less. So they can't conduct the electricity. So this is why insulators are not good conductors. They are not conducting electricity. So what is the reason behind the conductivity of electricity in metals and mixed metals? They have the ability. Okay, they have electrons. They have free electrons with the ability of moving randomly, moving around. So they can transfer the current. They can help to transfer the current. But when you come for insulators, that ability is not there. Okay, so there's a clear difference between the conductors and insulators. When you take this marker won't be having electrons, free electrons to move around, something like the metal. Okay, when you're gonna take an iron rod will be having. Okay, but marker is not like any plastic material, wood, asbestos sheets. Okay, you take nothing. They don't have these electrons to flow like. Okay, so their conductivity is less. So they are insulators. Electric insulators. That is another point. Heat conductors, heat insulators. That's a different part. Anyhow, this is connected. We already learned about it. Okay. So now you see electric conductors, electric insulators are there. Then who is there between? Semiconductors. These semiconductors you take, they have the atoms. They don't have free electrons. They have no free electrons at the beginning. But slight change in temperature. You increase the temperature. Even at a smaller rate for these semiconductor materials identified so far. Okay, you increase the temperature slightly. What happens? The bonds between the atoms break. One atom to another atom bond. How are they bonded? By the electrons, right? They are bonded. So the bonds are broken because they are interatomic. Interatomic bonds are very weak. You learned about intermolecular forces. Intermolecular forces means in between the molecules. Water molecule to water molecule. The bond is intermolecular. Interatomic means between the atoms. That may be ionic or covalent. Okay. So these interatomic, actually the semiconductors are falling under covalent bondings. So these interatomic bonds are very weak. So even a small temperature rise you give, this bond breaks. This bond breaks. When the bonds are broken, now you can understand the bonds are given by the electrons. When the bonds are broken, electrons can come out. Electrons can come out. Now these electrons coming out becomes delocalized electrons, the free electrons. So at this point, they can transfer the current. They can conduct electricity, but at a small amount. At a small amount. And they do have some terms and conditions as well. So accordingly, you see, this is how semiconductors do their work. They don't have electrons from the from the origin, but because of at a it's from the origin means actually we are taking it at 0 Kelvin. Okay, so this concept we are taking where they don't have electrons at 0 Kelvin. Okay, 0 Kelvin means, can you remember 0 Kelvin? Absolute zero temperature. So 0 Kelvin means minus 273 Celsius degrees. Okay, so the temperature that we are having, that we are in, it is about 30 degrees Celsius, right? So 30 degrees Celsius means it's more than 273 because 0 degrees Celsius means 273. Okay, so more than 20. So let's say 27 degrees Celsius we are adding up there. How much it is? That is 310 Kelvin. So almost 300 times more there. Okay, so 310 Kelvin like temperature we are in. So in such a temperature, anyhow, semiconductors will be having smaller number of electrons around. So these electrons let the current to pass at a fewer rate. Okay, so this is how we separate, we distinguish conductors and semiconductors. Is that point clear? Did you understand the point? Point by point we go. Okay, because this lesson is a bit confusing. This lesson will be a bit confusing if you don't learn properly, if you learn all at once. So slowly, step by step, part by part we go. And most of the times, these short notes are important for you to learn. Okay, clear? Did you understand the point? If you have a question, please ask. Okay, what we learned, the initial part are the conductors, insulators, semiconductors. The summary here, conductors, they can conduct electricity because of they have free electrons. They have free electrons. Okay, so insulators, they don't have these free electrons or very less, so they can't conduct electricity well. Semiconductors at a higher temperature, okay, more than 0 Kelvin degrees, not degrees, more than 0 Kelvin, 0 Kelvin. Okay, more than 0 Kelvin. So simply you take it, Zainab, 0 Kelvin. 0 Kelvin is the absolute zero temperature. Now we are not in 0 Kelvin. We are in 30, about 30 degrees Celsius means more than 310, about 313 Kelvin. So it is anyhow coming up with the theory because at a high temperature. At a high temperature, they will have electrons. How it happens with the diagram, we will learn. Okay. So they can transfer the current at a small rate. They are the semiconductors. That is a summary here. Okay. Any questions, right? Any questions? Okay, let's put the topic. Unit 11, electronics on a writing book. You will get the diodes in the next class, inshallah. Right? Unit 11, electronics. Electronics. Take this note first. Take this note, only this note. Okay? Don't write this. Because below these three words, we have to write a small point. So keep a space between them. Bit expanded, take these arrowheads. Keep a space between them so we can write a small note there. Quickly take these three words. Okay, so let's write that down below the conductors. Below the conductors. The materials, these materials can conduct electricity well. These materials can conduct electricity very well. Below the conductors. These materials can conduct electricity very well. Okay. And below the semiconductors, they can conduct a small amount of current, a small amount of electricity. They can conduct a small amount of electricity. They can conduct a small amount of electricity. Okay. And insulators, they can't conduct electricity. Insulators, they can't conduct electricity. Insulators, they can't conduct electricity. They can't conduct electricity. Okay. These materials can conduct electricity well. They can conduct a small amount of electricity. They can't conduct electricity. They can't conduct electricity. Okay. So let's write a small question there. So the example is given here. You can see semiconductors, silicon, germanium. Silicon, germanium, these are the major parts here. Okay. And I told you semiconductors are totally we are going to focus in this step. And then insulators examples are there: ebonite, polythene, plastic, wood, asbestos, glass, all this paper, all these steps. Right. Now, why do materials conduct electricity? Let's write there. Put the topic. All right, a question there. Why do materials conduct electricity? Why do materials conduct electricity? Why do materials conduct electricity? And let's write the reason as well. The reason behind the ability to, don't write everything, only the first three lines. Okay. Only the first three lines you have to write. The reason behind the ability to conduct electricity is the ability of some of the electrons in the atoms of such materials to move freely within the conductor. They are what we term as the free electrons or delocalized electrons. So the word delocalized is very rarely used. But in case if it is used, remember that is the free electrons. Okay. Write those three lines. Once you write the first three lines, you have to draw this. You have to draw this diagram. Okay. And better when you mark the electrons, so draw the diagram using a pencil or a black pen. Mark the electrons using a different color pen and show the arrowheads accordingly. So it would be clear to you what you wrote. Okay. So this happens because they are not like very tightly bound. So to the nucleus, these electrons are not very tightly bound. That is why they come out. That is why they come out. So you can see it is given there down. Electrons in the outer shells of conductors act in this manner since they are not tightly bound to the nucleus. Since interatomic bonds, covalent bonds, I told you between the atoms. So especially between the atoms of insulators are strong when you come for the insulators. But we spoke about the conductors. They have a weaker bond. So anyhow the electrons out. But here the insulators have got a strong bond. So those electrons can't come out. So there are very few electrons that are free to move. So because of that, they can't conduct electricity. They can't conduct electricity. So that's the reason. Okay. Write the first three lines and draw the diagram. Go ahead. And in between, if you have a question, please ask. Okay. And clearly, my concern here in this chapter specifically, it's a confusing chapter at some places if you don't continuously focus and listen. So if you miss any points at the moment, please ask to clarify and go ahead with the next. With doubts, don't go, you will miss. Okay, you will mess up with the lesson. Okay. It's a kind reminder. If you have a question or a doubt, stop me and ask at the point. Okay, clear? If you can't speak, at least a message, okay, a comment to the chat box. I hope you are done with the first 3 lines. So you can copy the diagram. You can copy the diagram, okay? So what's there inside the bracket? Delocalized. Delocalized. Okay. What is delocalized? Delocalized, they are the free electrons. Free. Delocalized electrons means free electrons. Okay. Delocalized electrons means free electrons. They are the electrons have come out of the nucleus, out of the shells, out of the shells. Because of they are not very tightly bonded to the nucleus here. This happens in metals, okay? The conductors. Right. Shall we go to the next part? Done drawing the. What is indicated through letter I? Simple E refers for electrons. I refers for electric current. I refers for electric current. I refers for electric current. Yeah, that's good. If you have questions like that, please forward. But make it at the moment we are discussing, okay? Right. So we are moving into the next part now. Semiconductors. So all metals conductors. Basically, the metals when you are taking, okay, metals commonly they are conductors. They are conductors. And some metals are very good conductors, some are relatively less. Something for an example, when you are taking copper and iron. Copper is a very good conductor. Why? By the material combustion, when you compare, copper has a very lower resistance. This is coming from the grade 10 theories. Resistivity you learned, right? By the material composition, copper has a very lower resistivity. So if the resistivity is very less, conductivity is very high. Relative to copper, iron has a higher resistivity, so the conductivity is less. Okay, right. So semiconductors. What are these semiconductors now? Semiconductors, they are the materials. We can't say metals actually. They are the materials who can transfer a small amount of current. Okay, that happens because of this. Now, basically, the semiconductors are taken from the group 4 elements. Which group elements? Group 4 elements. Group 4 elements, right? So, group 4 elements, but we don't take carbon here. Okay, starting from the third period, sodium, magnesium, aluminium, silicon. Can you see silicon? Silicon we are taking as the major example here. So, look at this silicon setup. Silicon, it is the 14th element, right? Silicon is the 40. So, these points, you better just write it down. Okay, take the topic silicon. Put the topic semiconductor, take it as silicon. Okay, because these points are what you basically you forget. When you forget these points, you mistake with all the lessons. Silicon, when you are taking, it is Si. It is the 14th element. Atomic number is 40. Silicon's atomic number is 40. So 14 means 2, 8, 4. This is the electronic configuration. That means how many electrons are there in the outer motion? How many electrons are there in the outer motion? This is the valence shell electrons, right? Valence shell means outermost shell electrons. So you see, silicon having only 4 electrons in the outermost shell, and if it wants to become stable, it has to take another 4 electrons to share. Okay, it has to share 4 more electrons. Okay, so because of this, what it does, when you take the silicon material, only silicon. So now look at this silicon when you're gonna take. Okay, this silicon, only 4 electrons are there in the outermost shell, right? Slowly we'll put. Look at this. 1, 2, 3, 4. And what it does, it has to bond with another atom obtaining 4. But it can't do like that, because it's naturally sharing 1 to 1. 1 to 1. So it takes electron from another silicon. 1. Can you see? And another silicon here. 1. And another silicon here. It gets 1. Another silicon here. 1. Okay. So you see, 4 silicon atoms are sharing electrons with each other. So altogether 8 electrons have been completed. So can you see 8 electrons are completed? Why? It has got 2, 8, 4. So 4 electrons were there. It gets 1 to 1 share. Then what about these silicon? They have also got 4. So 1 is given here. 2, 3, 4. Same way here. 2, 3, 4. And another silicon, let's say now here. 1, 2, 3, 4. Now it is also bonded. And this silicon also having. Now what they do? They also make the bond like the same. So 1, 2, 3, 4. And here another silicon. So like what happens you see here, they are making a lattice. They are making a lattice of silicon. They are making a lattice of the silicon, sharing the electrons in such a way. So ultimately you can see between each silicon, a pair of electrons have been shared. One pair of electron has been shared. So that means there will be no balanced electrons. Exactly when you take the silicon material, if it is a continuous everlasting silicon material you take, you can't find out electrons balance. But the thing is, everything we do have a limitation, right? The last point anyhow will be having. So something like this, imagine this is the end of one point. So end of the one point, only one electron will be left over there. That means it is ready to join hand with another silicon. Another silicon comes here, will be joined. So that ability is there. So such a way, imagine the whole board I can roll like, okay, connecting to one another. We don't have a limitation here. Now, this is how the silicon structure is formed. Silicon lattice is formed. And what type of lattice it is? Is it an ionic lattice or else atomic lattice? It is an atomic lattice. Ionic lattice means it is formed by the ionic compounds, right? And this is a covalent compound, right? So it should definitely be, we don't say a covalent lattice, we name it as an atomic lattice. So this is an atomic lattice. And the bonds between them are not that much strong. It's weak. So Even a small temperature change you do. A small temperature change you do. You increase the temperature. I told you at 0 Kelvin. From 0 Kelvin, when you increase the temperature, what happens? What happens? Electrodes, the bonds will be broken. When the bonds are broken, when the bonds become weaker, electrons have the ability to come out. Electrons have the ability to come out. So some electrons come out. Some electrons come out. Now you see, this is the origin. Clear about the origin, right? Okay. It's clear about the origin, right? Now, from this origin, what happens? What happens? Let's say from the origin, okay, you are going to increase the temperature somewhat. From that 0 Kelvin, you are increasing the temperature. Okay, you are increasing the temperature. So before the structure is what I have given in black here. Right? Now let's say you increase the temperature. When you increase the temperature, some of the electrons come out. Let's say I'm taking these electrons out here. Out here. So I'm using a red color pen to show that. This electron come out. Once the electron has come out, here the electron is not present. Now it is something like a person being seated in a chair goes out. Person goes out, the chair is left over with no one. Understood? The chair is free. Like the person here is electron, the chair is the space. Once it gone off, the electron has gone off, this becomes a free space. It becomes a free space. So the electron came out, we name it as the free electrons, and these are the holes. These are the holes. So you see here, like, let's say the electrons are coming out. These electrons will be there between the space while leaving a free space. Leaving a free space. So these electrons, red color, they are the free electrons. They are the free electrons. And the holes are there, the free space, they are the free holes. Free holes. So there are two people here, two particles here. One is the free electron, the other one is a free hole. The person seated on chair goes out, person also free, chair is also free. That is the concept here. Okay, so some of the electrons have come out like that. You see now, accordingly, in a semiconductor, when you increase the temperature, in a semiconductor, when you increase the temperature, what is the possibility? More electrons go out. More and more electrons come out of the lattice. Okay, so when more electrons are coming out, look at the chain, look at the link. You increase the temperature in a semiconductor. We are speaking about the semiconductor. In a semiconductor, when you increase the temperature, electrons come out of the lattice, of the bond. When electrons come out of the bond, more electrons become free. More the free electrons, they can transfer more current. They become, conductivity. Their conductivity is happening there. These are the semiconductors. These are the semiconductors. So did you understand about the semiconductors here? Is that semiconductor part clear? Is it super clear? Tell me first. This part, if you clearly understood, the rest of the parts gonna be very easy. Okay, I'll give you 2 minutes. Just have a look. Have a look and repeat to yourself. Okay, repeat to yourself what happened here. If you still have a problem, please ask. I'm giving completely 2 minutes. Just give it in your own. Make it in your own. Yeah, we have some questions, right? So, delocalization occurs when there is a temperature change in both conductors and semiconductors. No, not that point. Okay, not that point. We speak about the semiconductors only here. That's a good question, right? We speak about only the semiconductors. So the next part I'll be taking this actually. That is, Semiconductors, okay, in semiconductors, you increase the temperature. I hope these short notes are fine, okay, without writing long statements. When you increase the temperature, free electrons increase, correct? When you increase the temperature, free electrons increase. You got the point? In semiconductors, I'll come back to the other questions also. In semiconductors, when you increase the temperature, free electrons come out. Free electrons increase. When the free electrons are increasing, then what happens? Current conductivity increases. That means I is current. I is current. Electricity conducting ability increases. That means current will be passing. Current will be passing. So temperature, let me take it as T. In semiconductors, temperature is directly proportional to the current. Got it? This happens in semiconductors. This happens in semiconductors. Temperature is directly proportional to conductivity. But in conductors, when you come for conductors, when you come for conductors, you increase the temperature. You increase the temperature. Resistivity increases. The resistance increase. This happens in conductors, not in semiconductors. Okay. So this happens in conductors. You increase the temperature, resistance increase. Resistance increase. When the resistance is increasing, you know that resistance and the current are inverse proportion. According to V equals IR theory. V equals IR theory. You increase the resistance, current decrease. So the current conductivity decreases. Can you see? When the resistance is increasing, current will be decreasing. So automatically here when you come, temperature is inversely proportional to the current. Temperature is inversely proportional to the current. That means you increase the temperature, current decrease. You decrease the temperature, current increase. So free electrons are not connected here so far. This is going up with resistance. So that is the difference between semiconductors and conductors. And moreover, in conductors, when you increase the temperature, that the heat is increasing, right? This heat energy is okay increasing the resistance, sort of resistance. So this reduces the current. Okay. I hope you got that question. Questions answered. So why do electrons come out? Yeah, Riska. Why do electrons come out when you come for semiconductors? I told you these electrons, okay, they are bonded right between the silicon atoms. I hope others will be also maybe having this question. So listen. Silicon to silicon atoms, they are bonded by electrons. So these electrons are not strongly bonded. They are weak bonds. So whenever you come for weak bonding, if you increase the temperature slightly, there is a possibility that the bonds could be broken. And that is what happening here. When the bonds are broken, electrons come out. Give me a thumbs up if you got the answer for your question. Okay. And next, so do you want to write this in? Yeah, we have to write. I'll instruct you how to do it. So if they were balanced, what do you mean by if they were balanced means? What is that? If they were balanced, discuss. So won't the other electrons move? No, all electrons at once they won't come. One by one here and there they can come. That depends on their bonding and all. Okay. And that depends on the increasing of temperature, right? If you got the answer for your questions, give a thumbs up. So why specifically you took silicon? Silicon is the main example for whom semiconductors, and there are some other examples also like germanium and all, but germanium is not there within our periodic table, right? So the only example and the most preferred example within our first 20 elements in that periodic table, silicon is what there. That is why silicon we are using together, right? Hafiz, what do you want me to explain again about the free electrons and holes? Right. When the electrons are coming out because of the temperature increase, when you increase the temperature in semiconductors, electrons come out, leaving that space free. So that the space becomes a free hole. Electrons coming out becomes free electrons. Those free electrons are what we termed earlier as delocalized electrons. Okay? Got the points? Will you send the recording? Yeah, just we started, right? So what if we decrease the temperature in semiconductor? Opposite. If you increase the temperature, free electrons are increasing, right? Then what happens? When you decrease the temperature, free electrons will be decreasing. Okay, because moreover, then the point is 0 Kelvin. 0 Kelvin means that is the absolute zero temperature. Absolute zero temperature. That is the temperature where the particles are not vibrating at all. So absolute zero temperature, zero. We take this point in the black color one, but we have marked here 0 Kelvin. At 0 Kelvin. So there is no motion, no vibration. So you can't actually reduce the temperature more than that. That is the point. Okay, so that is the point there. You can't decrease the temperature more than 0 Kelvin because 0 Kelvin is the final temperature. Final lowest temperature is 0 Kelvin. Minus Kelvin we don't have. Okay. So what if the temperature increase and the electron doesn't come out? So usually when you come for semiconductors, it won't happen. Depending on their bond, there is a minimum energy needed to take this electron. If you provide that energy by increasing the temperature, somewhat they come out. They would come out, right? So if they are not coming out, that means you haven't reached that point of temperature. So you have to keep on increasing the temperature, right? Yeah, we'll send the recording, but you have to be online, okay? You have to join this continuously. So semiconductors have weak bonds. Yes, they have weak bonds. Since the silicon to silicon like examples, they have the weaker bonds. So after all the electrons left, what will happen? After all electrons left, what electrons? Electrons left between the silicon atoms. Did you mean that, Zainab? Did you mean that? After all the electrons left, that means is that all the electrons come out? That possibly won't happen. That possibly won't happen because if to happen like that, we have to give a very big temperature. Okay, so there may be some other conversions happening. So because even a small temperature change we are doing, electrons will be coming out, right? And what is our motive here? To use it as a semiconductor to pass the current. So that what do you call the aim? The motive would be complete. Okay. So can we use another material to fill the free hole and create a new material? Exactly. Okay. Not a new material. Actually, we are using that to make a different structure. We'll come to that point. Usman, we'll come to that point. We are going to fill it up with some others. Right? Yes. Zainab, I hope you got the answer. That's good. When you ask these questions, okay, everyone would be learning about that. And you would be more understanding about what the real picture is. Don't go up with questions too. Okay. Done with this, right? This part is clear. Okay, so what I have given in red color, look at this, free holes and free electrons. Now look at the point, free electrons. Okay, free electrons are minus, right? So the free electrons, they are the negative charge carriers. What are they? They are the negative charge carriers in semiconductors. And free holes relatively becomes positive. Because when the electrons were there at that point, no plus minus charges. That's neutral. Once the electron came out, that is something like when you remove out electron, it becomes plus sign. Likewise, when the electrons have come out, leaving the space free, the free hole act as the positive charge carriers. The positive charge carriers. So remember, electrons are the negative charge carriers. Carriers means to transfer. Okay, like a vehicle you are using. Vehicle is used to transfer the passengers from one point to another. Likewise, electrons become the negative charge carriers. Free holes become the positive charge carriers. And this is also one difference between the conductors and semiconductors. Earlier, one difference we discussed along with the temperature change. Now, the other difference is in conductors, only free electrons are there. Only free electrons are there. Only negative charge carriers are there to transfer the current. Only negative charge electrons are there to transfer the current in conductors. But when you come for semiconductors, both electrons and holes are there. So what happens? They do have both the negative and positive charge carriers. They do have both the negative and positive charge carriers. Both of them are there. Okay, you understand that? So Semiconductors, they do have both negative, positive charge carriers, but in conductors, only negative charge carriers are there. So this is also one difference between them. Is that points clear? Points clear? Anyhow, these diagrams and all will be there on your tute also. But than memorizing like that, it's better we write it down. Okay. So when you are writing, take the point. This is how it happened. Don't copy from here. You have seen the way I drew, right? I started from here and I counted one by one by one. So go ahead like that. Use a black or blue color pen or a pencil and mark these in red color or any other color pens. Okay. So start from here. Start from here. This is the point. Okay. Start from here. So this is the valence shell electrons. Okay. So this is the main part you have to remember. That means about the silicon's structure. Please note it down. Start from here. Take it separately like this. Mark this and then this part you have to do. Hurry up, please. And you can see the way I'm marking, the same black color I'm using. Bonds in silicon at 0 Kelvin. This is not okay. 0 Kelvin. 0 Kelvin. Bonds in silicon at 0 Kelvin. That is what I have given in black color. Initially, the black color was filled. Okay. Bonds, actually, that is complete bonds. Complete bonds. There is no breaking bonds. Okay. But when you come for the next part, which is marked in red color, you can use two different colors. Okay. These, some of the bonds have been broken, releasing some electrons. Releasing some electrons. So, some bonds are broken. Some bonds are broken, releasing some free electrons at a high temperature. Releasing some free electrons. Some bonds are broken, releasing some free electrons at a high temperature. Right? I can write it down. You can't see, so I wrote it continuously. So I have given black color. Complete bonds in silicon because there is no bonds broken. Completely all the four pairs were completed. Okay. This is 0 Kelvin. Oh, not okay. 0 Kelvin. 0 Kelvin. At a higher temperature, more than. Sorry? Anyone ask anything? Right? So please note this down first. And then this part. Then you can write this blue color one. Look at the order. First this one. And this diagram with the statement. Okay. Then you write this down. The free electrons and free holes, the negative positive charge carriers. Afterwards, you can take this point. Please note it down soon. And in between, if you got any questions, please ask. Is that okay now? Khadija, hope it's okay now. Oh, right there. Some bonds are broken. If you can't see this, some bonds are broken. Releasing some free electrons at a high temperature. Releasing some free electrons at a high temperature. So how do we know that the free holes are positive charge carriers? Yeah, that's like this. No? Now, when the electrons are being removed, okay. So electrons become the negative. We know electrons are negative. Why? You see now, it's something like this. Imagine now, this is neutral. It is neutral. Okay. You have the electron and the hole. Both of them are there. Now it is neutral. When this electron is going out, it is carrying out the minus charge, right? And it was neutral, right? It was neutral. And only the minus charge gone out means definitely the remaining should be a positive charge. Okay, so that is how the holes become positive. And moreover, it could be seen with another theory, that is when a potential difference is connected, you could observe electrons will be moving from negative terminal to positive terminal. Holes will be transferring the charges from positive terminal to negative terminal. The flow would be from positive to negative. So definitely positive to negative, someone is moving, that is definitely a positive charge. Okay, Mara? So how scientists observe that electrons are broken when heat is increased? It may be something like this. Now when you increase the temperature, okay, they can transfer current, right? And we already know that if the current has to be transferred, there should be electrons. There should be electrons. So current to transfer, electrons must be there. And a semiconductor which was not conducting electricity, when increasing the heat more than zero, starts to conduct electricity, means definitely it should be leaving out more electrons. Okay, so that is how electrons are transferring. And moreover, they could have used some sort of electroscopes, right? Just like where they earlier days they used electroscopes, cathode ray electroscopes, to find out the presence of these electrons, protons. So likewise that could have used. Okay, hope we are writing down. I'll give you some time, but I need the note to be perfectly written, okay? Because again, when you refer and revise, you should not be having any problems over there. Okay, and moreover, when you are writing this, if you need some other words in your own, you can write. You can write. And take it in another color pen so you can remember this is your note. Yes, write the temperature note as well, because that's a comparison between. So take all of them separately, one by one. I think that's enough time, right? Enough time? Shall I get to the next part? Right. So you see that was about the semiconductors. So have a look now. This is what initially it was. You can see here. All right. And then what happened? As we have discussed now. Because of the temperature change, can you see some of the electrons have come out? So actually electrodes are marked in pink color here. Okay. So some of the electrons have come out. You can observe. Some of the electrons have come out. You can observe. Right. So once the electrons have come out, that the space becomes a free hole. So several electrons are given here. That is because of the weaker bond. Now, accordingly, in semiconductors, conduction of electricity is contributed in two ways. Right there. Write that statement. In semiconductors, in semiconductors, conduction of electricity is contributed by two ways. In semiconductors, conduction of electricity is contributed by two ways. What are they? Number one, free electrons. Free electrons. So in front of the free electrons, let's write there. Free electrons act as the negative charge carriers. Free electrons act as the negative charge carriers. Free electrons act as the negative charge carriers in front of free electrons. The next one, free holes. Free holes. Right there. Free holes act as free holes act as free holes act as now positive charge carriers. Free holes act as the positive charge carriers. Positive charge carriers. Okay. Positive charge carriers. All right. So you see, when an electric potential difference is applied across a semiconductor, I told you, holes move from the positive to the negative terminal, while electrodes move from the negative to the positive potential. And the conventional current, electric current, also flows from positive to negative. Accordingly, the charge carrier, we discussed about that. Metallic conductors. The charge carriers that conduct electricity are the negatively charged electrodes. Only negative charge carriers are there in metallic conductors, in conductors. We discussed about that, right? In semiconductors, see, they are the negatively charged electrons as well as the positively charged holes act as the charge carriers that contribute towards the conduction of electricity. Umar, which is the part you want me to repeat? These two. These two. Free electrons. For free electrons, you have to write act as the negative charge carriers. For free electrons, you have to write act as the negative charge carriers. Free holes, you have to write act as the positive charge carriers. Free holes act as the positive charge carriers. Positive charge carriers. Right. Okay. Osman, which is the statement you want to repeat? Have a look on this. Let's say this is the semiconductor. Okay, this is a semiconductor. Now I'm going to connect this semiconductor with a potential difference. Earlier we took this diagram from conductor. Okay. A semiconductor I'm taking. Previous slide. That is what I repeated, Osman. Negative charge carriers act as the, sorry, electrons act as the negative charge carriers. Free holes act as the positive charge carriers. Okay. Let's see what happens here. Now, this is a semiconductor. And you have the holes. You have the free holes. And free electrons are there. Free holes and free electrons are there. So remember, free holes. Okay, this is the positive terminal, right? And this is the connection at positive. Negative terminal connecting the negative. And free holes, free electrons, both of them are there. Free electrons, free holes, both of them are there. Okay. So remember, free holes move from positive. Now, this is the positive connection, right? Positive to negative, plus to minus. Okay. Electrons flow from, this is the negative connection, negative to positive. Negative to positive. Okay. And the current when you take, current flows from positive to negative. This is a positive connection, right? Positive to negative current flows. Current flows. And this is one reason why we term the positive, the free holes as positive charge carriers. Because positive charge carriers are what? Moving from plus to minus. Plus to minus. Did you understand that point? Is that point clear? In semiconductor, conduction of this part. This part. You can copy it. Right. We'll note this down. We'll note this down. This part. Take it as in semiconductors. In semiconductors. And all what you are learning, you have to remember, because all these we are going to use. That's what this diagram I'm keeping here. With this diagram, only the next part we have to go now. Can I please explain the blue diagram? Yes, here, this is a semiconductor. I'll just consider this as a semiconductor. Let's say this is a semiconductor. It is a semiconductor. In a semiconductor, free holes are there, free electrons are there. Okay. And they won't move. Okay. They won't move means, okay, we'll take that point later because that's separately covered. They will move when you are connecting with a potential difference. So let's say the positive terminal you are connecting here and the negative terminal you are connecting here. Positive when you are connecting here, positive to positive will be repelling, right? So these are positive charges now. So positive to positive will be repelling. So free holes will be moving from positive terminal to negative terminal. And electrons are minus, right? Electrons are minus. So negative terminal to negative charges will be repelling. So negative terminal connected here, negative charges, electrons will be repelling. So electrons move from negative to positive. Okay, so what you have to remember here, electrons flow from negative terminal to positive terminal. Free holes flow from positive terminal to negative terminal. And the conventional current, that means electric current, flows from positive to negative terminal. Okay, hurry up, please. We have some more to do. Right. So look at this now. Semiconductors, we take two types of semiconductors are there. What are the two types? Look at this. One is called intrinsic, the other one is called extrinsic. Intrinsic semiconductors, extrinsic semiconductors. Intrinsic semiconductors, they are the pure state of group 4 elements. Pure state of group 4 elements. Extrinsic semiconductors, when group 4 is doped with another. What is the meaning of that? Doped with? No? Quite an odd meaning given. No? Doping. Doping. So, not something coming to your mind. Doping here it refers for mixing. Mixing, combining physically. A physical combination. So, a group 4 element when mixed up with another element, maybe group 3 or group 5, either side, because 3, 4, 5, right? Either 3 or 5 they are mixing. It is called extrinsic semiconductor. It is called extrinsic semiconductor. Have a look here. Look at this. So, what is intrinsic now? Intrinsic refer for, okay? Intrinsic, this refers for pure state of group 4 elements. Okay? Pure crystalline state of group 4 elements. Who is the major example? Silicon, germanium. These are examples. Silicon, germanium are main examples. Main examples. Okay? And extrinsic means. Extrinsic means. Now, let's say this group 4 element, either silicon or germanium, either silicon or germanium, it is doped with a group 3 element, or else it is doped with, no, nice word, group 5 element, doping. Either group 3 element or group 5 element. A doping with, the previous or the after. Right, 3, 4, 5, right? So, such a doping is called extrinsic semiconductor. Extrinsic semiconductor. And depending on with whom the fourth group element is doping with, mixing with, okay, mixing with. There are two types of extrinsic semiconductors. What are the two types? One is called P type, the other one is called N type. Positive type and negative type. Positive type and negative type, two types of semiconductors are there. Two types of extrinsic semiconductors are there. How it happens? Look at this. Now, let's say I'm going to take group 4, okay, group 4 combined with group 3. Okay, let me write there here. Group 4 element combining with group 3, mixing with group 3. This forms a positive type. What type? Positive type extrinsic semiconductor. This forms a P type, positive type extrinsic semiconductor. When it is group 4 and group 5, this is forming a negative type extrinsic semiconductor. A negative type extrinsic semiconductor. What are they? Group 4 with group 3 gives positive type. Group 4 with group 5 gives negative type. Negative type. So how it happens? Look at this. Now, let me fill up this once again. This diagram. Okay, with no any red color ones. It's totally filled. Now this is silicon, right? Have a look properly. Okay, this is silicon. Now I'll take the first example. Let me take the first example. N type. N type. I'll take N type. Now, when you're gonna take this N type, okay. Group 5. Group 5 means let's say after silicon we have phosphorus. Sodium, magnesium, aluminum, silicon, phosphorus. Let me take that phosphorus here. What I do, silicon is already there and phosphorus comes to dope with silicon. No, phosphorus comes to dope with silicon. Dope with silicon means mix with silicon. Mix with silicon. So I'm going to apply a phosphorus here. Who is phosphorus? Phosphorus is the 15th element. So 2, 8, 5. Phosphorus is the 15th element. 2, 8, 5. So you can see 2, 8, 5. That means 5 electrons are there in the outer shell. So phosphorus, when you are taking, it has 1, 2, 3, 4, 5. 5 electrons are there. There are 5 electrons in phosphorus. When you're going to dope phosphorus here, somewhere, imagine now I'm going to keep phosphorus here at this place. Look at this property. Whom I'm going to take now? I'm going to replace silicon because phosphorus, when it comes, one place will be given for phosphorus. So phosphorus also will be mixing in between. So what happens? Let me take this off now. This part, this silicon I'm going to take. When I'm taking this silicon off, its electrons also have this electron 2, 3, 4. So all these electrons I have taken out. Now I'm going to keep this phosphorus here. Look at this, what happens. Phosphorus comes off with how many electrons? 5 electrons, right? Okay. Now it gives 1 here. It has to join hands, so otherwise it can't be staying inside, right? 2, 3, 4. Now you see, only 4 electrons can be given. Only 4 electrons can be given. Then what about the remaining electron? Remaining electron will be there inside. Remaining electron will be there inside the material, within the material as a free electron. What electron? Free electron. So when one phosphorus atoms come like this, one free electron will be there. Phosphorus won't be doping as only one, right? A number of phosphorus atoms come here when we are doping up. So 5 phosphorus atom means 5 free electrons. 10 phosphorus atom combines like this within the silicon lattice. 10 free electrons will be there. So you see, more and more phosphorus atom is connected here, more and more free electrons it gives because it has 5 electrons, where it has to combine only 4. So every phosphorus comes up with an excess of electron. So when phosphorus combines here, it provides an excess electron. It provides an excess electron to the setup. Providing electrons means it's donating electrons. Donating electrons. Now, who are the ones to donate electrons among these two now? Is it group 3 or group 5? Group 5. Because group 5 are what having 5 electrons in the outer shell. Group 5 are what having 5 electrons in the outer shell. So these ones, when they are combining with silicon, they donate electrons. They donate electrons. So when the electrons are donated like this, what is the charge the electrons are having? Negative charge. Electrons are having a negative charge. So when more electrons are donated like this, electrons having a negative charge, the negative charges are added to this setup. So this becomes negative type. This becomes negative type N-type extrinsic semiconductor. This becomes the negative type N-type extrinsic semiconductor. So this is how N-type is formed. This is how N-type is formed. So simply, when a group 5 element is doped here, group 5 comes up with 5 electrons, but it can share only 4 electrons. So the remaining, the leftover 5th one is there here as a free electron. So every time when a group 5 element comes here, atom comes here, 1 electron in each of them is in excess. Okay. So when, I'm repeating it. When every atom, every group 5 atom is connected over there here. I'm repeating. Every group 5 atom is connected over there here. 1 electron will be left over. 1 electron will be left over as a free electron. So only 1 atom I'm taking. So let's say I'm taking another atom. That phosphorus atom will be also a free electron provided. So these electrons given in excess, we term it as donating. Okay, donating the electrons. So who are donating electrons? Group 5 elements, right? So these group 5 elements, we name them as donor atoms. What atoms are they? Donor atoms. They donate the atoms. Group 5 elements, they donate the atoms. Donor atoms. Okay, donor atoms. So donating the atoms, they give negative charges into the setup. So this extrinsic semiconductor becomes negative type, N-type extrinsic semiconductor. Clear? This is how N-type forms. This is how N-types form. So you see, group 5 with group 4, who is combined? Group 5 is combined. First part. Okay. what they do? They have 5 electrodes. Let me write like 5 valence electrodes. Valence shell electrodes. Points to remember. Okay. So donates 1 electron in excess. Donates 1 electron in excess. So are called donor atoms. And since electrons are negative charges, semiconductor, it is named as N-type extrinsic. It is named as N-type extrinsic. Did you understand? Is that point clear? Related to the N-type. So what I explained now, I have given in points to remember. All these are there on your tube, but in paragraphs. Okay, because it's explaining the description. So further, I have given you in points for you to remember. What is it? 5 valence shell electrons are there in group 5, donates 1 electron in excess. So they are called donor atom. They are called, what atoms are they? Donor atoms. Who are they? Group 5. So group 5 are called donor atoms. Okay. Who are they? Group 5. Okay. Group 5 are called donor atoms. Since electrons provided are negative charges, now this is named as N-type extrinsic. It's called N-type extrinsic. Okay. Right. Like the same. This is the first type, right? What is the second type? Second type. I think we don't want to draw the diagram. It's clear to you. These diagrams are there on your tube. Okay. But we need this node. Now look at the group 4 combined with dope with a group 3 element. Group 3 element. What happens if it is a group 3 element? What happens if it is a group 3 element? In a group 3 element, somewhere like, let's say, shall I take this off? This part shall I erase? It's clear, right? This part is clear, right? I'm going to the next part. Fine. Speak. Shall I take this over with the next diagram? Anyone writing this? No one. Okay. So now what happened? It was silicon. I'm replacing the silicon with the third group element. Somewhere let me take the boron. Boron is third group. Hydrogen, helium, lithium, beryllium, boron. Boron is third group. That means 2, 3. 2, 3. 3 electrons are there. 1, 2, 3. Boron comes only with how many electrons? 3. 1, 2, 3. Now the part is clear to you. You see, needs 4 electrons, but coming up with lack of 1 electron. So this space where it is connected only 3, while the fourth one has no electron from boron, it becomes a free space. It becomes a free space. Again, boron is a third group element. Third group elements have only 3 electrons. We need 4 electrons connected elements, but it's coming up with only 3 electrons. So 3 to 3 electrons bonded. The fourth one to get bonded, no electrons provided by the B, the third group element. Okay. So is it a free space or free hole? This free space is what we name as the free holes. Okay, the free space here is what we name as the free hole here. So you see, a free hole means is it a negative charge or a positive charge? Positive charge. So a group 3 element when doping with group 4, it provides positive charge carriers because it's lack in an electron. So it is ready to accept atoms, accept electrons. It is ready to accept an electron. There is a chair free, it's ready to accept a person to be seated. Okay, so earlier it was donating atoms, group 5 coming up with excess 1. Now it's coming up with the third one is coming up with let in one electron. So it's ready to accept that left one. So what happens here? Look at this. Group 3 elements. Group 3 elements have only 3 valence shell electrons. They have got only 3 valence shell electrons. Okay. So they can't donate because they have a free hole. They have a free hole. So makes a free hole. Because of that, it is hence ready to accept electron. So they are called acceptor atoms. Who are called acceptor atoms? Group 3 elements. Who are called acceptor atoms? The group 3. Group 3 atoms. Group 3 atoms are called acceptor atoms. Acceptor atoms. So now you see, since holes are positive charges, it is named as, right? It is named as P type. It is named as P type extrinsic. This is how the name came. It is named as the P type extrinsic. So can we mix with other groups? No. Basically, 3 and 5 are what mixing up. To make, actually this mixing is done to result in some others. What are the some others? Positive type and negative type, because these positive type and negative type we are going to connect with another diagram. You know, one after the other it goes. Okay. I hope it's clear. Don atoms, accept atoms, point by point. Okay. From here, could you please take the note? Please take the note from there. So what is the significance of the two types of semiconductors and during what occasion are they used? So two types, P type and N type. Okay. So these P type and N type collectively we are going to use as PN. P type, N type connected together with a semiconductor, pure state semiconductor, we are going to use it as a PN. We name it as a PN junction diode. A diode or a diode you could have heard of, right? A diode or a diode, the name you could have heard of. That the diode or diode is made up of these PN junctions. And there are some others, transistors, okay? Some other electronic devices are there. Can you remember I started the lesson with this word, electronic gadgets, electronic appliances. So these electronic appliances are basically formed from these junctions. And where are we using? In the motherboards. In the motherboards, where are the electric circuits, the fundamental circuits are there. In all our electric devices, we have them. I mean, most of them where we want to control some stuffs. Are you done? Are we done? Yes, we did a big part. Fine. So accordingly, this note, you see, this gives you the complete idea about what you have learned now. And this is what we discussed. Can you tell me this? Is it a P type or N type extrinsic? Is this P type or N type? Yeah. Is this P type or N type? But I'm screening on. Just because of the letter P, don't tell me. Okay, think about that. It is phosphorus. Is it P type or N type? You have to see what it is providing to the lattice. Is it a free electron or a free hole? Yes, comment on please. You can see it's providing a free electron, right? You can see it's providing a free electron. So free electron provided means it is an N type. Okay, it is an N type. Muhammad, it is an N type. Okay. Why is that? Because can you see it's giving a free electron here, right? This is a free electron. Free electron is provided. Free electron provided means, okay, electrons provide donating one electron. Okay, it is N type. N type. What about this now? The same examples we discussed. What about this? Is it N type or P type? Is it N type or P type? So definitely you can see it's P type, right? Okay, P type. Why P type? Because it's providing a free hole. Free hole. Free hole means a positive charge. Okay, positive charge. So more it is connected, more positive charge carriers are there. So that is P type. I hope it's totally clear. Fine. Okay. So any questions up to this before we go for the next? Before we go for the next, do you have that capacity? Next part is the combination of both this P and N. How many of you are ready to go up with? Now you understood well. With that understanding, if you are going, it's easy for you. That's my point. You understood well about this part, right? With this, when you are going further, it's easy, but you have to focus. Shall I continue? Anyhow, we have time. But I need everyone to stay until the last, okay? Until the last point, you have to stay. You can't go. Fine. That's great. So we're gonna continue. Next point, I told you P and N we are going to connect. P and N we are going to connect. So we take it as PN, which you term as the PN junction. PN junction. Right? PN junction. So PN junction diodes. That is our next topic. What is the topic? PN junctions. PN junctions. So what is this PN junction? What is this PN junction? Now you see, you learned about this P and N both, right? P and N both you learned. Okay. How? Now, two types of semiconductors we learn. Two types of semiconductors we learn. Okay, what are the two types? One is intrinsic, the other one extrinsic. Now, I have a group 4 semiconductor. I have a group 4 semiconductor. And we learned earlier group 4 connected with group 3 is positive type. Group 4 connected doped with, actually the word is doped. Group 4 doped with group 5 is negative type. What if both of them are doped? No? What if both of them are doping them? Right? Mixing up. What's happening then? Let me take the group 3 here. 3 doping up with 4 in one side and 5 doping up with 4 in the other side. Now what happened? There will be 2 points, 2 ports here. Okay. 3 to 4 makes P type. So this junction is P type junction. P type junction. 4 to 5 makes N type. 4 to 5 makes N type. So 3 to 4 makes P type. 4 to 5 makes N type. So what happens now? This becomes PN. P type and N type becomes PN junction. PN junction. Right? So this is how PN junction is formed. This is how PN junctions are formed. One side the third group, the other side the fifth group, the middle is the pure state intrinsic semiconductor, that is the fourth group. So that means it will balance. It will balance means there is a sort of change happening. That change is what we are going to learn. Okay. So you see 3, 4, 5, 3 parts are there. 3, 4, 5, 3 parts are there. Now, let me take this like I'm going to take a diagram. That is this diagram expanding. Look at this. Positive type means whom we have. We have holes, right? Positive holes are there. Positive holes are there. Negative type means who are there? Electrons are there. Okay. So positive type and negative type we are referring by these holes and electrons. Now, if you ask me, sir, why did you take it as 4 rows and 4 columns? That is not must. Okay. That is not must, but when I am using 4, it's easy to explain and easy for you to understand. Okay. So 4 columns, 4 rows. It's not must, just an example. Now, the point here, this becomes the junction where both of them are meeting, right? So this side is the P type, positive type holes are there, and this type becomes the N type, negative type electrons are there. Negative type electrons are there. Okay, electrons are there. So holes are there to one side, the positive side. Electrons are there to the other side, negative side, and this becomes the PN junction. So this is the junction now. Actually, this is the junction now. PN junction. PN junction. Now, let me remind about a sort of theory. Diffusion, can you remember? What is diffusion? Diffusion means the particles moving from high concentration to lower concentration. High amount of particles to low amount of particles. Okay. High amount of particles to low amount of particles. Particles can move. Particles can move. So now here in this diagram, you can see positive side is full of positive holes. Negative side is full of negative electrons. Negative electrons. Okay. So what will happen for the silicon in this situation? Silicon is what in the center between. Why? Because silicon to boron makes P type. That P type is there here. Silicon to let's say phosphorus makes N type is there. So between that only the bond is made. The connection is made by silicon. Okay, wall is made by silicon. Now the point is, I told you, particles can move from high concentration to low concentration. Now, free electrons are there more here. So free electrons try to move to the positive side. Okay, free electrons try to move to the positive side, while the holes try to move to the negative side. While the holes try to move to the negative side. So there will be a sort of diffusion happening. Holes move from p type to n type. Electrons move from n type to p type, but not everyone. So this is a diffusion. What is happening here is diffusion. High concentration to low concentration. But the thing is, why are they moving? And another point is, because this is plus, this is minus. Plus and minus attract. Plus and minus attract. So, and they move because of the concentration difference. Now look at this. Once they transfer, look at the points clearly, okay? Let me take the next diagram. Without taking all in one diagram, I have to draw it again and again. What to do? Now, take this one, 5. So you see, 1, 2, 3. 1, 2, 3, 1, 2, 3, 1, 2, 3. Now you may ask me, where is the fourth one? I'll speak about that. Okay. Now you see, I told you, everyone won't pass. Now the column of holes here, let's say all these holes I'm taking to the other side. So holes have gone here. Positive have gone to the negative side. Positive have gone to the negative side. And the negative come to the positive side. Negative come to the positive side across the layer view. Across the layer. Now the problem is, okay, once the positive have come to the negative side, that is a sort of attraction there. Okay. The next positive, they are also trying to move. Now one set of positive have gone. Next set of positive also try to move. But the problem is, positive, right? These are positive. And these are also positive. Positive to positive, can they move into the same side? Can't, right? Why? First row of positive have gone. One reason, concentration difference. The other reason, because of the attraction towards the negative. And the second column of positive, when they try to go, they can't move because the other side already gone. Positive ones are repelling them. They are not attracting them. Since there is a repulsion, the second column of positive can't go there. Same way, electrons have gone to the other side, right? Electrons are minus. These electrons are also minus. So the second column of electrons, when they are trying to go there, the first column who have already gone to the positive side, they repel. Because minus to minus, they repel. So the second column of electrons, they can't go there. So that is something like negative ones are trapped in the positive side. Some of the positive ones are trapped in the negative side. So furthermore, they can't transfer because of the repulsion. Got that point? Is that point clear? No, you can compare with the social life also, right? That happens. No? Sometimes it happens. You are trapping, right? Right. Okay. So you see, this is what happening here. So further, there is a negative point in the positive side, and there is a positive, okay, positive line in the negative side. So look at this. This positive, I'm going to take it off. Look at this. This positive, okay, I'm gonna mark it as, you can see here, I'm going to mark it as a longer terminal to indicate that is plus, because it was positive holes, right? Positive. These negative ones are there. I'm going to take them off, and I'm going to mark it as a shorter terminal. Shorter terminal means negative. So you see what we did now, that the positive holes we took out and we labeled it as the plus terminal. Negative, we named it as a minus terminal. And now you see it becomes a cell. It becomes a cell. Okay, why cell? Because there are positive and negative terminals formed. But the problem is, usually when you are connecting the cells, positive to positive and negative to negative, you have to connect. Positive to positive and negative to negative, you have to connect. Then only the cell provides a proper potential difference. Then only the current will pass. Here the problem is, to the positive side, you are having the P type here. To the P type, you have the negative terminal. And you are having the N type here. And to the N type, that should be negative terminal, but you are having the positive terminal. How? Because of the transferring of these charges. Now, this battery, the dry cell, the cell, okay, the battery we term it because of the charges. This battery becomes a hypothetical battery. We say hypothetical conditions are there. No? It is called a hypothetical battery. What battery it is? A hypothetical battery. Why hypothetical battery? Because of it is not in the correct connection. It is right opposite. Nothing could be done with the usual flow. And moreover, what happened? They were distracted because of positive to positive, negative to negative, right? So this layer becomes a distracted layer. And this layer, we name it as depletion region or depletion layer. What is the layer? Depletion region or depletion layer. So this potential difference, the difference between this plus minus in the wrong sides, we name this as hypothetical battery, and this gives rise for a potential barrier because the potential difference is in the wrong way. So this is called a potential barrier. Potential barrier. That means a gate for you to cross out. So if you want to cross out the path, you have to definitely break the gate and go. That is the idea. Potential barrier, there is a barrier for the flow of current. If you want to somewhat flow the current, you have to break this potential barrier. So this potential barrier you have to break. Okay. So now let's say if this person is there, the fourth group is there. If this fourth person is silicon, if this fourth person is silicon, it may be silicon or germanium both, right? It may be silicon or germanium both. Let's say if this fourth person is silicon, then you know how much is this potential barrier. I told you there's a gate, you have to break the gate. So if this fourth person to form up this PN junction was silicon, the potential barrier formed in these plus minus terminals will be 0.7 watts. How much is the voltage? 0.7 watt. And if it was germanium, the gate formed here, the barrier formed here will be 0.3 watt. What do you mean by that? I told you, if you want to cross over the gate, you have to break the gate. So if you want to cross over the potential barrier with silicon, then you have to give a voltage more than 0.7. More than 0.7. And if it was germanium here, to cross this potential barrier, you have to give a voltage more than 0.3. More than 0.3. So that is the idea here. Is that clear? So if it was silicon, the potential barrier you have to break here is more than 0.7. Then germanium more than 0.3. So then the remaining will be no use. No, we are using. Okay, we are using connecting with the potential difference. Now I'm coming to that point. Okay, I told you to break the gate. You can't break the gate all alone. You have to get the support of both the sides. Connecting with an external supply. So accordingly, now you see this is the depletion layer. This becomes a hypothetical battery providing the potential barrier since it is in the wrong side. Now, if you want to cross it out, you have to break this layer. You have to break this. How to break? You have to reduce the depletion layer. So to reduce the depletion layer, you have to give an external support. So this external support will be an external power supply, an external voltage supply. So this external voltage supply, when you are connecting to such a PN junction, this is a PN junction diode, right? For a PN junction diode connected with an external voltage supply, we name it as biasing. What we name it as? We name it as biasing. BIAS, biasing. Okay, so biasing a PN junction means connecting an external voltage supply to a PN junction. PN junction. Clear? Can you please take a screenshot of this? You can copy it later. Take a screenshot. I'll go up with the next one. Since we are running out of time. Okay. Now you see what happens. I'm going to bias this. I'm going to bias this. So this structure is what I'm going to take now. Okay. I'm going to bias this. So one biasing is the correct biasing. The other biasing is the wrong biasing. Okay. One is the correct biasing. The other one will be the wrong biasing. Wrong biasing. Let me take the wrong biasing first. Okay. Which is called reverse biasing. What biasing it is? Reverse biasing. Reverse biasing. Reverse biasing means, look at this, what happens. Okay. Same diagram. I don't know, it's number of times I have to take the same diagram. I have to do. Wow. Now I do have this setup. 1, 2, 3. 2, 3. This is how it was, right? This is how it was. So hold on for a while, okay? You finish it up and go, right? So now you see, I'm going to connect this. I'm going to connect this, an external supply, but I'm giving the wrong connection. What do you mean by the wrong connection? Now this is the positive side, right? This is the positive side. Okay, P type. And this is the N type. Okay, N type. And positive side should be connected with positive, right? But I'm connecting with negative. Positive, I'm connecting with negative. Negative should be connected with negative, but I'm connecting with positive, longer terminal. So you know, usually when you are connecting the electric supply, plus to plus, minus to minus. So this is plus, you are connecting minus. This is plus, you are connecting minus. Wrong. Wrong connection. So in this way, you know what happened? Now look at the point. Positive comes here, right? Current comes here, let's say. Now positive to negative, what happened? Positive to negative, what happened? Quickly tell me. Is it positive charge, right? Plus means, positive terminal means positive, right? Okay. Positive when it comes here, electrons are negative. Positive to negative, what happens? Attracting or repelling? Quickly tell me. Is it attracting or repelling? Hurry up, give me a word. Plus to minus, simply positive when it comes here means plus. Electrons minus. Plus minus attract or repel. Attract, right? So what happened? These electrons move towards plus. You are connecting the plus here. You are connecting the plus here. When you are connecting the plus over there, electrons move towards plus. Electrons move towards plus. You understand? You understand? Electrons move towards plus. So I'm showing you by taking this one line to show that electrons are moving towards. Okay. So plus attracts the electrons. Electrons are moving towards them. So let me mark it. Electrons are moving towards them. Okay. So now here the minus, right? Minus connected to the positive side means minus to plus, what they do? Tell me. Minus to plus, what happens? Same thing, right? Attract, right? Minus to plus also attract. So minus to plus when it is attracting. Minus to plus when it is attracting. Now what happens here? You can see further. Okay. These positive holes move to this side. Then positive holes are not there. Not there means they are moving towards. Now, what happened for the layer here? What is happening for the layer here? Can you see the layer is increasing, right? The gap is increasing, right? Okay. So you can see here what's happening. The potential barrier layer there, that is increasing. Can you see? It was the negative terminal and this was the positive terminal. You can see the depletion region layer. Depletion region layer increase. Can you see that? Depletion region layer gap is increasing. Now, on a long jump, when the jump layer deadline is increasing, is it easy to run? Is it easy to jump over? It's hard, right? Okay. So it has to be less in length. So now this has been increased means there is no way the current could be passing. Okay. Okay. So if you continue, will they lose everything? Yes. Okay. But the thing is, it's useless. Why? We don't want that actually. Right? So there is no current passing here. So here, current is 0. Current is 0. There is no current flowing. There is no current flow. Understood the point? No current flowing here because the depletion region has been extended. Can you see? This is the I'll write here. This is the depletion region. Depletion region is increased. So in reverse biasing, because of the wrong connection, depletion region broadens. It becomes broader. So no current passes. No current passes. Second one. We'll end up with this. Forward biasing. What is forward biasing? Forward biasing. You can now imagine what happens there. Okay, you can imagine what happens over there. It was, I'll start from here. 1, 2, 3. 1, 2, 3. Right? Now you are going to connect it with the correct connection. Correct connection means this is the P type, you are connecting the positive terminal. N type, you are connecting the negative terminal. Correct? Can you see that? Plus minus correctly you are connecting. Plus minus correctly you are connecting. When you connect them correctly, now you can imagine what happened. You can see depletion region reduces. Why? Now plus 2 plus they push out, right? You are connecting the plus 2 plus terminal, plus 2 plus they push. They are pushing on. Go on. It's saying go on forward. So what happens? It gives another layer of holes because it's pushing forward. Minus to minus also repel. So it's also giving another layer, right? So you see, they are giving another layer. But still, there is a gap between. But still, there is a gap. There will be a gap. Okay, there will be a gap now. Still, there will be a gap. Okay, still, it's similar to magnets. Yes, exactly. This side becomes a magnet like. Okay, so now still there is a gap. Why the gap? Because you haven't reached these points. You are giving a connection, a correct connection you are giving, but less than 0.7 for silicon, less than 0.3 for germanium. Connection is correct, plus 2 plus, minus 2 minus correct. But you haven't broken the gate. You are close to the gate. Correctly, you have put it on. Key lock is correct. But you haven't given the minimum range yet. So if it is silicon, 0.7. Let's say for silicon, you are giving a potential barrier more than 0.7. Less than 0.7 if you are giving, let's say you are connecting a bulb here, bulb doesn't light. Equal to 0.7 if you are giving, you can see the bulb is ready to blink. More than 0.7 you are giving, let's say 0.8 at least you are giving, bulb lights up, you can see, because the current flows. So you see what happens here. If voltage, we take it as bias voltage, VB, bias voltage. Okay. So if the bias voltage is less than 0.7, no current. Less than 0.7, current is 0. Okay. Current is 0. Let's say if the bias voltage is more than 0.7, I'm speaking about the silicon, okay? More than 0.7, then current is not 0. Current flows. You understand the point? If the bias voltage is more than 0.7, current flows. Then you know what happened? Even this border becomes closer. Depletion region already less. Now the depletion region come closer, only this line will be there. only this line will be there. It comes closer. Coming closer, it's getting into one another. They help to transfer the current. They help to transfer the current. So you see, if it is silicon, bias voltage should be more than 0.7. Then there is bias voltage should be more than 0.7. Then current is not zero. Not zero means there is a current. If germanium, how much you have to give? Minimum 0.3 you have to go across. So more than 0.3 when you are giving, you can transfer the current. So this is how PN junctions are working. Then where do we use? We are using these, giving a smaller voltage, giving a smaller biasing voltage to turn on the setup. We are using them. And where we want to pass the current only in one direction, where we want to pass the current only in one direction, we are using these PN junctions. Okay, because you see now, in this forward biasing only current is passing. Okay, forward biasing only current is passing. Reverse bias more than 0.7 you are giving. Will it be passing the current? No, because reverse bias means wrong connection. Reverse bias means wrong connection. Even you give more than 0.7, that won't be current passing. Okay, so whenever you want to protect the current and let the current to flow only in one direction, you have to connect a PN junction. Okay, PN junction, because it lets the current to flow only in one direction. It lets the current to flow only in one direction. So what is the direction? When you come for the symbol, this is the symbol of PN junction. Okay, this is plus, this is minus. A triangle you can see with a slight line in this way. This is plus, this is minus. Plus and minus. Plus and minus. Plus is called A anode, minus is called K cathode. This is the symbol. Without AK we are using, without plus minus also we can use. And remember, the current passes only in this direction. This is the direction current pass. Opposite direction, this is something like the stop mark. It doesn't allow the current to pass in the opposite direction. It doesn't allow the current to pass in the opposite direction. So this is the symbol of ohm diode. Symbol of diode. So all what we are speaking about is PN junction diode. Okay, this is the symbol of diode we are giving. And moreover, in the real time, how do you find out? This is how you can find out a small cylinder light. A small cylinder light, you can find out this gadget. This gadget. Okay. But how do you find out which is A and K? Closer to the K, you have a small ring-like structure. You have a small ring structure which is white color or silver color ring. Okay, a white or silver color ring is there. That is the cathode. The other side becomes the anode. That means to this side you have to connect the positive terminal. The other side you have to connect the negative terminal. The other side you have to connect the negative terminal. Did you understand? Is that clear? So whenever plus 2 plus, minus 2 minus connected, forward biased. Plus 2 minus, minus 2 plus connected, reverse bias, where there is no current passing on. Take a screenshot. Take a screenshot. You understand? Oh. Did you understand the whole part? Super clear? Right? We took a long time actually. Okay, very long time to finish up this part. And I'm very excited to see that all you people were staying. Okay, all you people were staying, at least, most of the people were staying until the last moment, even if it is online. So I hope the lesson was clear and very, connective. One another, it's connective. If you are focusing, you can very well understand. Okay. So is that totally clear? Give me one word. Just give me one word. Is that totally clear? Yes or no? Fine. Fine, alhamdulillah. Right. So, I told you, one of the hard chapter, confusing chapter. So, part by part we took. Okay. Those who are having problems, please make sure you are going up with the recording. Okay, please make sure the others also go through the recording. I will share the recording, inshallah. Okay, take a time and go through the recording. Look at your tune. Look at your note and go ahead. And please note this down. Take a time, one by one, note it down on your book, on your writing book where you completed the notes. Okay, it's gonna be very easy for them. Okay, so first part of the lesson we are done with about the PN junctions, and revise what you learned. Refer the next part from your textbook before the next class. Okay, right? So depletion region definition, no need. So just you simply remember, because of the potential barrier, the gap between the two sides. Okay, fine. So please make sure you refer them, revise them totally before the next class. Next class, as usual, on Saturdays, inshallah, we'll be having. And reminding about 17, we are having a sort of 2 seminars actually. Okay, 2 seminars. One is for grade 10, 16 chapter. Where basically we're going to speak about the chemical reaction types, chemical equations, and mainly reactivity series. Okay, and the theories related to that. That is from 9:30 to 1. We'll share the flyer. And basically, I want to inform you related to 8, 9, 10 chapters. Heat changes, heat, electricity. We're going to have a seminar for calculations, question and answers to revise comprehensive. That is on the same day, 17th, 2 to 5. 2 to 5. I have already shared you the flyers, I guess. You got, and I will also share within my announcement groups. Okay, so please make sure to join to revise. 50% discount is given for the class students. Share it with all your friends to join and be benefited, those who want a clarification in that chapter with the formula related stuffs. Okay, so we have question and answers we are going to do, and before that, before the lessons and come, then it's gonna be very easy for you all. Yeah, it's open for all. Anyone can join because it's a sort of paid seminar. For them, it would be 100%. Class students only 50%. It has to be. Okay. Plus project proposals. I can remember that I told you we have to provide it today. Okay. Somewhat we couldn't make it. You have given another week time. Please do complete it. Don't give me messages. I won't reply. Some of them they have. Okay. I won't forget. Right. Okay. Some of them they have texted, but I didn't reply. I told you, right? You have to do it. So next week you have to definitely provide. You have to submit it. Okay. Plus, I didn't forget another thing. You were supposed to have an exam. Paper is prepared simply just because of you people. Okay. And in fact, last night only I just prepared the paper. Okay. So next week, definitely you are having that paper. Somewhat, we couldn't make it physical today. Next week, inshallah. So automatically you are getting 1 more week time. Please get prepared further. Next week during the paper class, you are having your paper. What about the paper class today? We are having it maybe around 6:30. Shall we start? Yeah, project proposal next week. I told you. Umar, you are not listening at all. Huh? Shall we start the paper class around 6:30? Getting a small break? Fine. 6:30, come back with another thing. Another link. Yeah. Okay, fine. So I'll share the link. Please make sure to join that online class. Okay, for paper. Fine. See you then. We did great. Okay. See you then in the next session. Until then, have a small break. Ending up.